When we think about gravity, we usually imagine it as something fixed. Earth's gravity is 9.8 meters per second squared. The moon's gravity? 6 times weaker at 1.6 meters per second squared. Mars? About 3 times weaker at 3.7. Simple, right? But here's something surprising. Gravity doesn't always work the way you think. Let's talk about Saturn. Saturn is about 100 times bigger than Earth. Yet its surface gravity is only about 10.4 meters per second squared. That's nearly the same as Earth's. Even more shocking? On Jupiter, the largest planet in the solar system, you'd feel only about 2.5 times heavier than you do on Earth, despite Jupiter being 1,000 times bigger. Why is that? The key lies in 2 factors: mass and size. Gravity depends on how much mass a planet has and how far that mass is spread out its radius. Saturn, for example, is massive, but it's also incredibly large and made mostly of gas. Its density is so low that it would float in water if you had a tub big enough. Because Saturn's mass is spread out over such a huge volume, the pull of gravity at its surface, which is really just the top of its thick atmosphere, is relatively weak. Jupiter, while much denser than Saturn, has the same balancing act. Its enormous size dilutes the strength of its gravity at the cloud tops. This is why, despite being a giant 318 times the mass of Earth, you'd only feel about 2.5 times heavier there. So gravity isn't just about mass, but density and the distance from the core. Now let's get back to Earth. Does Earth's gravity get stronger the deeper you dig? And what is the highest possible gravity on Earth? The answer is more complex than you might expect. At first, yes, gravity does increase as you dig deeper. That's because you're getting closer to the Earth's core, which holds most of the planet's mass. As you move closer to a large mass, the gravitational pull grows stronger. But this increase doesn't continue indefinitely. Once you start getting really deep, something interesting happens. The mass above you starts to pull you upward. Imagine digging halfway to the center of the Earth. Now you have as much of the Earth's mass pulling you from above as you do from below. These forces start to cancel each other out. The result? At the very center of the Earth, the gravitational pull is 0. You'd feel completely weightless because the forces from all directions cancel each other out perfectly. So where is gravity strongest on Earth? It's actually at the core mantle boundary, about 2,800 kilometers beneath the surface. Here, gravity reaches its maximum strength of 10.7 meters per second squared. After that point, gravity decreases as you move toward the core until it hits 0 at the center. But let's take this even further. Gravity isn't just shaped by planetary size and density. It can also fluctuate due to the composition of the land beneath your feet. The planet isn't a uniform ball of rock. It has mountains, valleys, dense mineral deposits, and even underground oceans. This creates tiny variations in the local gravitational field, known as gravity anomalies. For example, there's a mysterious region in the Indian Ocean known as the gravity hole, where Earth's gravity is significantly weaker than normal. Scientists believe this could be due to remnants of an ancient ocean that sank into the mantle millions of years ago, subtly affecting mass distribution. On the other hand, in places like Hudson Bay, Canada, gravity is slightly weaker because the region is still rebounding from the weight of massive glaciers that covered it during the Ice Age. When I was a kid, I intuitively thought gravity was this invisible force pulling on every single atom in my body. But now I realize that gravity isn't a force at all. It's not like a magnet pulling you down. It's something much stranger. You see, according to Einstein, you're actually constantly falling. The only reason you don't feel like you're falling is that the ground you're standing on is stopping you. The force you feel isn't gravity. It's the ground pushing back up against you, keeping you from following your natural motion through space-time. It may not feel like it, but the space around you is very curved. And for some reason, we cannot tell the difference between curved space and non-curved space if there's nothing stopping you. If you were free to follow that path, you wouldn't feel any force at all. This is why astronauts in orbit experience weightlessness. They're still under the influence of Earth's gravity, about 90% of what we feel on the surface. But because nothing is stopping them, they are weightless. But here's what's fascinating. Even though Einstein showed us that gravity isn't a force, Newton's understanding of it was still remarkably accurate for his time. Newton imagined gravity as a force pulling on objects, and he used this idea to explain why the moon orbits Earth. He even theorized that if you could shoot an object fast enough, it would fall around the Earth forever, creating an orbit. But Newton's view of gravity had a blind spot. If you think of gravity as a force, why don't objects in free fall experience it as a force? Why don't they feel the pull? Einstein was the one to answer that question. He called it his happiest thought. He imagined a man falling. The man wouldn't feel any force as he fell. He wouldn't feel the pull of gravity. In that moment, Einstein realized that gravity wasn't what Newton thought it was. It wasn't a force at all. Instead, it was the shape of space-time itself. This was the breakthrough that led to Einstein's theory of general relativity, a theory that not only explained gravity but also predicted things Newton never could have imagined: black holes, gravitational waves, and the bending of light by massive objects. Einstein's insight surpassed Newton's genius not by disproving him but by building on his work. Without Newton's laws and the foundation he laid, Einstein wouldn't have been able to revolutionize our understanding of gravity. And this brings us full circle to the point about human progress. Every discovery, every insight, is built on recorded history. Without schools and without the ability to pass knowledge from one generation to the next, we'd have to start from scratch every time. Newton himself famously said, "If I have seen further, it is by standing on the shoulders of giants." The most mind-blowing thing about gravity is that it's the weakest of all the fundamental forces, yet, paradoxically, it might have the greatest potential. Alone, the gravity of a single atom is practically non-existent. Even if you add a kilogram of atoms together, their combined gravity is still almost imperceptible. Every atom in existence bends the fabric of space-time, creating its own tiny gravitational well. But individually, these dents are so minuscule that they're practically meaningless. Like a drop of water in the ocean that is space. It's only when you gather trillions upon trillions of atoms, forming something as big as a mountain, an asteroid, or a planet, that these effects start to add up and become noticeable. The larger the mass, the deeper the dent in space-time, until you get something so extreme, like a black hole, that nothing can escape its pull. And here's the real mystery. We still don't fully understand gravity. Unlike electromagnetism, which we can manipulate with technology, or the nuclear forces, which power the sun and atomic bombs, gravity refuses to fit neatly into our theories. Despite being the force that governs the movement of galaxies and the shape of the cosmos, we have yet to discover the particle that carries it, the so-called graviton. And unlike other forces, which weaken and disappear over short distances, gravity never truly fades. Its influence extends forever, just getting weaker with distance but never reaching zero. It has infinite reach, yet we can't grasp its true nature. It may just be the most mysterious force in the universe. Let me know your thoughts in the comments below. Thanks for watching, and see you in the next one.